Hi, everybody, and welcome back to AP Physics 2. We have finally finished our review of optics and modern physics, and now we begin reviewing fluids. After that, we'll move on to thermodynamics, electrostatics, circuits, and magnetism. So here we are. We're in it. It's crunch time. The exam is coming. Welcome back. Today, we're talking about density and pressure, the first two units of fluids. As always, we're going to start with a quick lesson overview. We'll tell you how the lesson will proceed, and then we'll do our daily warm-up. Now, typically, that's the part of the lesson where we pick up the question that we ended with last lesson. And then we work through that, get you all warmed up to go. We proceed into what you need to know to be successful on the fluids question of this AP Physics 2 exam, followed with some guided practice from the AP Physics question bank, and then a debrief and summary to make sure that you picked up all of the important topics and skills that you're going to need. And then we'll do some AP exam practice, some questions that we'll leave you with that you can start with tomorrow. Some homework, I suppose. I am Joe Mancino from Glastonbury High School in Glastonbury, Connecticut, and it is great to be with you doing fluids.
And I'm Brendan Eaton from Reedy High School in Frisco, Texas, and it's going to be a good lesson today. So let's just go through a quick overview of what we're going to talk about today. The first topic is density and how mass, volume, and density are related. And we're also going to talk about density versus radius.
Afterwards, we'll talk about pressure in a fluid and the forces exerted by that fluid on things in that fluid. How we live at the bottom of an ocean of air. How pressure is a force exerted on an area. We'll talk about atmospheric pressure and gauge pressure and combine those into the idea of absolute pressure. Afterwards, we'll talk about Pascal's principle and how pressure is transmitted through a fluid.
And you should already know Newton's third law. You may know it as opposite and equal reaction, that type of thing, but we're going to talk about force pairs today and how that plays in fluids.
By the end of this lesson, we're hoping you can determine the density of an object and understand how pressure varies with depth in a fluid, and that you know the difference between gauge pressure and absolute pressure. Finally, we're hoping that you know Pascal's principle and why it's useful and what it describes.
All right, skills that we're going to address today are articulating reasons that scientific explanations and theories are refined or replaced, make claims and predictions about natural phenomena, connect concepts across topics, apply mathematical routines to quantities that describe natural phenomena, and re-express key elements of natural phenomena across multiple representations.
So like Mr. Eaton said, we have a great big day coming, but before we dive into it, make sure that you know these dates. If you are assigning these videos for your students and you're an educator, these are the dates that you need to know and what to assign when. If you're a student looking to customize your AP review, these are the dates that you need to know. We'll be sticking to this schedule. There won't be any changes in it. And we'll be proceeding right through the curriculum, 4 days on each topic. You may want to take a screenshot of this. And even if you missed the screenshot, you can always check back into the live stream. These will all be watchable in perpetuity.
All right, here's your first warm-up question for today. Cubes A and B have the same mass. Is cube C heavier or lighter than cube D? Take a second to think about that. All right, if cubes A and B have the exact same mass, what's different about cube A and B? I think you'll notice the size or the volume is different. Which one has a greater volume? That's right, cube A has a greater volume. And if it has the same amount of mass, that probably means that the density is just a little bit less than cube B. But the question is cube C heavier or lighter than cube D? Cube A and cube C look like they're the same material, and cube B and cube D look like they are the same material. Now, if I look at cubes C and D, those look like they have the same volume as well. So remember the first thing that I said, which one is more dense, A or B, yellow or purple? And I think the purple one's going to be more dense. Therefore, D is going to be heavier and B is denser. So is cube C heavier or lighter than cube D? I think cube D is heavier in this case. And it's all based on the density of those objects.
Now, we're hoping that you recall the relationship between density, mass, and volume. Yeah, I'm sure you learned it in your physics class and probably in a physical science class before that. So all four of these shapes are made from the same material, and their length, width, and height are marked on their sides. Can you rank them from the lightest to the heaviest? A ranking task like this is something that you would typically encounter on an AP physics test. So you should know how to do this. Well, like Mr. Eaton said, mass has to do with density and volume. In the last example, some of those objects had different densities. In this example, they're all made from the same material, which is your clue that they're all the same density. So the one with the greatest volume has the greatest mass. Volume is length times width times height. So if you think that shape D has the lowest mass and maybe shape B has the highest mass, you're in really good shape. All right. So what you have in front of you now is like a fish tank full of water, a big container of water with a rubber stopper jammed there in the side of it. And my question for you is, how does the force exerted by the stopper, exerted on the stopper by the water compare to the force exerted on the water by the stopper? So certainly if two things are touching, they are applying forces to each other. That stopper, where that black stopper is, it's pushing on the water and the water's pushing on the stopper. The important thing to note is the force exerted on the water by the stopper is equal to the force exerted on the stopper by the water. Now, you may have learned that for every action force, there's an equal and opposite reaction force, or for every action, there's an equal and opposite reaction, or something like that. That's Newton's third law. Newton's third law is the easiest to remember, but the hardest to understand. See, when we all learn it in school, my teacher certainly said, for every action force, there is an equal and opposite reaction force. It was described to me as if there were two forces, an action force and a reaction force. But the way that Newton said it, Newton said for every object acted on by a force, another object is acted on by that same force. In Newton's original description, the two objects have one force. It wasn't an action force and a reaction force. It was one force. Both of those objects share the same force. It's a mutual contact force between them. They are the same force, the same one force. So let's zoom in on that force and talk about what kind of force it is. Back in your Physics 1 course, you learned about what we call the force between things that push on each other. When objects push against each other, we call that normal force. Normal force is the pushing force that surfaces exert on each other. It is a perpendicular surface force because normal means perpendicular. They are synonyms. Normal doesn't mean typical or regular or everyday. It means perpendicular. So for the case of an object submerged in a fluid, just like that stopper is, the direction of the normal force is just perpendicular because normal means perpendicular. The fluid exerts forces on objects within the fluid, and the direction of that force is always perpendicular to the surface of the object.
All right, and now we're going to talk about what you need to know today. The first thing that you need to know today is density and how it expresses mass in terms of volume and density, and be able to quantitatively rank density, mass, and volume. You also need to know about pressure and forces. You need to be able to calculate the force a fluid exerts on an object, be able to identify where the force is exerted, explain the direction of fluid forces, calculate a gauge pressure and absolute pressure that a fluid exerts, and be able to compare pressures at different depths inside of a fluid. And with pressure and density, you need to be able to compare the density of two fluids based on the pressures that they exert.
All right, here we go. A fluid is any material that can flow, like a liquid or a gas. Most of the time in AP Physics, we refer to liquids, but occasionally you'll bump into a question about a gas. When we analyze fluid statics, that's going to be today and tomorrow, we'll be talking about density, pressure, Pascal's principle, and buoyancy. Then we'll talk about fluid dynamics. That's fluids that are in motion, that are flowing. We'll talk about the continuity equation, which expresses conservation of mass, and we'll talk about Bernoulli's principle and applications of that. That expresses conservation of energy.
And as you may recall from chemistry class, or any science class for that matter, that the Greek letter rho represents density. You should have seen this symbol before. And density is actually defined by mass per unit volume. So it's mass divided by volume. And also, rho times volume gives you what? It gives you mass. So just rearranging that equation, you can solve for the mass of an object pretty easily.
So here are the densities of some different materials. On the left side of your screen, you see the density of water. We usually round it off to about 1,000 kilograms per cubic meter. On the bottom right of your screen, you see the density of wood, the average density of an average species of wood, 750 kilograms per cubic meter. The density of mercury is 13,500 kilograms per cubic meter. The density of the middle of the sun is 150,000 kilograms per cubic meter. Kilograms per cubic meter is the standard unit of density, but that's also a really big number. A cubic meter of something is a lot of something. I couldn't lift a cubic meter of water. It has a weight on Earth of over 1 ton. So typically, we use convenient units for density based on however much of the substance we're talking about. A convenient unit for human-sized things is kilograms per liter. I think it's reasonable to think of a 1 liter bottle of water having a mass of 1 kilogram. A 1 liter bottle of mercury having a mass of 13.5 kilograms. Don't drink mercury. A 1 liter bottle of the sun having a mass of 150 kilograms. You can drink the sun. But could you smuggle a backpack full of gold? So for a lot of reasons, the answer is no. But in terms of physics, like, could you? Well, the density of gold is 19.3 kilograms per liter, or 19.3 thousand kilograms per cubic meter, 19,300 kilograms per cubic meter. I measured my daughter's backpack. It's 60 centimeters by 35 centimeters by 25 centimeters, which means it has a volume of that many cubic meters, which doesn't seem like a lot. Maybe my daughter could smuggle a backpack full of gold. So how would you figure out the mass of a backpack full of gold? Well, mass is density times volume. As an AP Physics 2 student, that's something you're going to need to know. Mass is density times volume. There's the density of gold times the volume of gold that would fit in my daughter's backpack. And it's, well, that's a lot of mass. That's over a ton. And she is a powerful young woman, but I don't think she can carry a ton on her back. So moving on. The other thing that you need to know as a smart AP Physics 2 student is a common question that the College Board asks about the relationship between a sphere's volume and its radius. It's been asked so many times that it's worth pointing out here that the volume of a sphere is given by 4/3 pi r cubed. That means a sphere's volume is proportional to the cube of its radius, or if you have two spheres, one of which has double the radius of another, the other sphere has 8 times the volume. So on the left, you see a sphere of radius r, and on the right, a sphere of radius 2r. Although the radius is doubled, that's an 8-fold volume increase. Mr. Eaton, tell us about this wrecking ball here.
Yeah, so we have a solid iron wrecking ball that's used to tear down buildings and cause a lot of fun destruction stuff. But if it has an 18-centimeter radius, and if we happen to know the density of iron, I bet you I could find the mass of the iron pretty easily. So I know the volume of a sphere is 4/3 pi r cubed, as Mr. Mancina just showed us. And if I start off with the equation of rho is equal to mass divided by volume, if I want to solve for mass, I just rearrange as mass is equal to density times volume. Again, that concept's going to come up a lot. So the volume is 4/3 pi r cubed. I know the density, and I know the radius. So very simply, I can plug in those numbers and get a mass of 190 kilograms for that iron wrecking ball, which is a pretty good mass.
Now, one of the most common mistakes my students make while they're typing this quickly is they square the radius in a hurry. You're so used to typing pi r squared for the area of a circle that sometimes in a hurry, you'll think pi r squared for the volume of a sphere. So just be aware of that.
That's an excellent point. That happens a lot to my students as well. All right, so our next mini micro topic is about specific gravity. And the specific gravity of a substance is the ratio of the density of that substance to the density of water. So it's the density of the substance divided by the density of water. Specific gravity doesn't have any units, which is kind of interesting because density does, but if you're taking a density divided by density, so kilograms per meter cubed or kilograms per liter, and divide it by kilograms per liter again, the units just disappear. So here's an example. The density of mercury is 13,500 kilograms per meter cubed. So its specific gravity is 13.5. How did I get from 13,500 to 13.5? Well, I think you might remember from earlier that the density of water is 1,000 kilograms per meter cubed. So 13,500 divided by 1,000 gives me 13.5. Now, specific gravity is also numerically equivalent to density in units of kilograms per liter or in units of grams per cubic centimeter.
Okay, so quick question. What is your specific gravity? Are you denser than water? Are you less dense than water? How many times denser than water do you think you are? Because ultimately, that's what specific gravity measures. How many times denser than water something is. So if any of you out there are swimmers, you know that humans are on average about the same density as water. If you fill your lungs with air, you can float pretty easily. But if you blow that air out, you sink. So your specific gravity, yes, your specific gravity is approximately 1. All right, true story. Last year, 16 trillion gallons of water fell on my hometown right here. And that's that many gallons, which is about that many cubic meters, 61 million cubic meters. The density of water is about 1,000 kilograms per cubic meter. So what's the mass of all the rain that fell on my town? It's a lot. You can figure it out.
All right, so moving on to pressure. That is a lot of water. All right, so dealing with pressure, I'm sure you've heard this word before. And of course, this is a review session, so you have. So pressure is just basically when a fluid is at rest, it exerts forces on surfaces within a fluid. So if you have a container of water, the fluid itself is exerting forces on objects within the fluid. So being a fluid, it can only exert forces perpendicular to its surface. As we saw in the warm-up, all the forces that were acting on the stopper were perpendicular. They were normal to that stopper. So the quick definition also of pressure is force per unit area. So force in newtons and area in meters squared. So pressure is simply just force divided by area. So getting force from that, which is a typical conversion that you need to make, or something that you typically solve for, is simply just pressure times area. All right, let's check out this box standing on a table. Now this box has dimensions of 3 by 2 by 4. So when it stands on a table, does it exert more force if it stands on face A, more force if it stands on face B, or more force if it stands on face C? So you need to think about what type of forces are acting on that box. Mr. Mancino, what were you about to say?
I was going to say, how do you know how much force a mass exerts when it sits on a table? How much force are you exerting on your chair right now?
Should be equal to your weight. So if I flip the box over, right now it's sitting on face B on the table, at least how I'm imagining it. If I were to flop that block over to where side A is touching the table, how much force is it pushing on the table with? It's probably still equal to the weight. What about face C? Do you think it's still equal to the weight? I think they're all the same in this case. Now here is a slightly different question. See, same exact box, it's on the same exact table. And does it exert more force if it stands on face A, face B, or face C? I read that slide wrong. This is about pressure. We even bolded that word on purpose. So yeah, okay. Anyway, so pressure, we know that pressure is force divided by area. Now from the previous slide, we said that the force was the same from all of those faces. So if pressure is force divided by area, when am I going to get the most amount of pressure? Is it when the area is large or when the area is small? I think it's when the area is small. So the smallest face, I have the biggest force on top of my equation. The force is the same for all three sides. I need the smallest amount of area to have the greatest amount of pressure. So which face has the smallest area? I think it's going to be face B. So 3 times 2 gives me 6 centimeters squared.
Okay, so we've talked about pressure in terms of force and area. Now we'll talk about pressure exerted by a fluid. We talk about the gauge pressure. That's the force exerted by the weight of the fluid above some point. Now, like we said a few slides ago, we live at the bottom of an ocean of air. And just like fish don't notice that they live in an ocean of water, people don't notice the fluid that we inhabit. We tend not to regard the air around us. When a container is full of air, we often say the container is empty, even though it is definitely full. But if you've been to different elevations, you've noticed that the higher up you go, you notice that the air is pressing less on your ears. If you've been to sea level and then been to a high elevation, you've certainly noticed the effects of that pressure. So gauge pressure measures how hard the fluid above you is pushing on you. Here's a quick derivation of gauge pressure. Near Earth's surface, it's easy to calculate gauge pressure because the air is mostly in equilibrium. So the fluid above you would be in equilibrium. So here inside the fluid, we're sort of imagining a vertical column. I'll open the front of that up for you. And that column of fluid is some height h tall. At the bottom of that column of fluid, the force due to the fluid pressure is just equal to the weight of the fluid column, just like that box on the table. Its force was the force the box exerted on the table was equal to the box's weight. So here we see a box of fluid, and the force it exerts on the bottom of that box is equal to its weight. Well, weight is mass times gravity. Mass is density times volume. Volume is area times height. So we do a little algebra, and you'll see there's a rho area times height times g in there. That term, that shaded blue term, is called the gauge pressure. No, it is not. The gauge pressure is defined as rho gh. That's the gauge pressure times area. My apologies. Rho gh is the gauge pressure. Here it is a little bit bigger if you want to take a screenshot and write that down. Gauge pressure measures the force per unit area applied by the fluid above the point where you're measuring.
And let's see how this works out mathematically. So the surface of the water in a storage tank is 30 meters above a faucet in the kitchen of a house. Calculate the gauge pressure at the faucet. Well, we know that the density of water is 10 to the third kilograms per meter cubed. And I think Mr. Mancino just gave us an equation that we can use. It's a change in pressure is equal to rho g delta h. That's straight from his derivation. So if I know the density of the fluid, which is 10 to the third, I know g is roughly 10, and I know the height of the water in the storage tank is 30 meters. All I have to do is multiply those three things together, and that gives me a pressure of 3 times 10 to the fifth newtons per meter squared.
Newtons per square meter. That is a mouthful. I wonder what we'll call that. Well, speaking of pressure, those of you who've been to the bottom of a swimming pool, or those of you who are divers, you certainly know that the deeper you swim, the more you can feel the water pushing on your ears. Well, that's the gauge pressure of the water above you pushing on your ears. But again, we forget that we live at the bottom already of an ocean of air. So on an AP Physics test, or just if you're wondering about pressure, we refer to the absolute pressure inside of a fluid as the sum of all the individual pressures stacked on top of you. If you've been under the water in a swimming pool, you've certainly felt the gauge pressure of the water. But right now, where I am, I'm experiencing the air pressure around me. I might not pay attention to it. If I had a pressure gauge, it would still say 0. But absolute pressure is the sum of all the pressures stacked up above me. Absolute pressure is the total pressure at any depth due to the weight of the fluid and any extra force exerted on the surface of the fluid. The absolute pressure, if you're underwater, is atmospheric pressure, the pressure from the air around you, plus gauge pressure, that rho gh term. So those of you who are divers know that you have to dive to a certain depth to experience 1 extra atmosphere of pressure. Well, 1 atmosphere of pressure is defined as 100,000 newtons per square meter. That's about the average air pressure at sea level. How far underwater would you need to descend to reach an absolute pressure of 2 atmospheres? Well, if the absolute pressure is the atmospheric pressure plus the gauge pressure, and atmospheric pressure is already 1 atmosphere, this is really asking how far would you have to dive for an extra atmosphere of gauge pressure? I'll spare you the extra math. I know you can handle powers of 10. Every 10 meters of depth in water is another 1 atmosphere of gauge pressure. So Blaise Pascal was a French mathematician, scientist, inventor, a truly fascinating person who I won't bore you with it, but the history of Blaise Pascal is unbelievable. Um, Pascal's principle, as it refers to fluids, tells us that extra pressure exerted anywhere on a fluid is transmitted undiminished to every other part of that fluid and to the walls of the container. Again, if you've been underwater, when someone dives into the water, or when someone jumps on a floating raft in a swimming pool, you felt the extra pressure on your ears. So right here, you see a two-dimensional cutaway of a three-dimensional. I tried to make a U-shaped tube with uneven sides. Those yellow rectangles on either side, those are movable pistons that can move up and down. When a force is applied to one of those pistons, when extra pressure is applied to the left piston, that extra pressure, that extra force per unit area is applied everywhere against the walls of that tube, against the other piston. Now, pressure is force per area. And what that means is that the extra force per area on the left side equals the extra force per area on the right side. The pressure on the left equals the pressure on the right.
So if you set those two pressures equal to each other, the force over area of the left and the force over area of the right, and rearrange for just the force on the right-hand piston, what you can see is a new expression for if we were to push on the left-hand piston to see how much force is coming up on the right-hand piston. This is a really common question given to by the College Board or maybe even by your teacher on tests. Now, the force applied by the right piston is directly proportional to the area of that piston. So looking at the diagram again, if you push with a small amount of force on the left-hand piston, what that yields is a very large force on the right-hand piston. And the way that this works has to do with conservation of energy. So again, conservation of energy, it sounds like it violates that. You get more force on the right than you put in on the left. That doesn't make any sense. But the piston on the left actually moves a greater distance when it's being pushed downwards. And if it's a small force with a big distance, what does that tell you about the right-hand piston? If conservation of energy has to apply here and there's work being done, small force, big distance has to give you a big force and small distance because the pressure is the same on both of those pistons.
For any of you who've had the experience of raising a vehicle using a floor jack, a hydraulic jack, the kind that you pump up and down, you've noticed that you have to move the jack handle many times over a meter-long distance to lift the vehicle even a small amount. Now, you can do it. You can apply a small force over a great distance, and the trade-off is that you get a great force over a small distance. All right, on your screen now, you see a fairly common setup that you've likely encountered as an AP Physics 2 student. A U-shaped glass tube that starts in equilibrium, simply filled with a fluid of known density, it's typically water. And then into one side of that container is poured in unknown fluid, raising the height of the water on one side and the height of the unknown fluid on the other side. I've drawn a schematic diagram of that. And oftentimes, this setup is used to see if you can figure out the density of the unknown fluid. Well, Pascal's principle tells us that the pressure here equals the pressure here. The pressure at any depth in the same fluid is the same. If the pressure weren't the same, we'd see flow. We'd see something dynamic happening. These fluids are at rest. So if the pressure on the left equals the pressure on the right, that means that rho GH on the left equals rho GH on the right.
All right, let's check out our guided practice questions for today. We're going to answer 3 questions. The first question is strictly about density. The second question compares density of different objects submerged in a fluid. And the third is a really interesting experimental question about the effect of temperature on density. So let's look at our first question. First question says, a gas-filled balloon has a total average density of 0.2 rho. The air surrounding the balloon has a density of rho. The balloon is released from rest in a constant horizontal breeze directed north. If air resistance is negligible, what is the shape of the path followed by the balloon? Well, I know from looking at just the prompt alone that the density of the balloon is quite a bit smaller than the density of air. And we know that less dense objects float on top of more dense objects. So in this case, when I release the balloon, I know it has to go up somehow, some way. But the problem is there's a breeze directed north as well. So if I have a net force, maybe upwards, because it's trying to float on top of the air, that's the ocean of air that's surrounding us, and there's a constant force from the breeze directed north, it looks like there's going to be a straight path towards the north and angled upwards. Kind of interesting.
Okay. There are, in this big fish tank, I took away the stopper. I didn't want anything to leak out. In this fish tank, there are 3 marked points, X and Y and Z. At which point is the density of the fluid greatest? So this is one of the assumptions that you can make in AP Physics 2. You will often be told, probably always told, that the fluid in each question is incompressible. And what that means is any mass of that fluid will always have the same volume. We can't squeeze that fluid into a more compact volume. So at which of these depths is the density greatest? Well, if this is an incompressible fluid, the depths are all the same. I just wanted to talk about the definition of incompressible fluid. Here's the real question. At the top of these 3 crowns, where is the pressure greatest? Now we know the density is greatest at every point. I know all these crowns have the same volume. They're on pretty similar looking strings in a fluid of uniform density. So where is the pressure the greatest? At the top round part of each crown, so you can have a point to focus on. Well, I know density affects pressure. I know gravity affects pressure. But the full relationship for pressure is gauge pressure is density times gravity times depth in the fluid. So crown Z, the one that is at the lowest depth in the fluid, is the one that experiences the most pressure. But what about now, when the volume of each crown is different? You'll notice the top of crown X is still higher than the top of crown Y, but crown Y is significantly larger than the other 2. Which of those crowns experiences a greater pressure at the top of the crown? We're focusing on just the top bit of the crown. Well, in this case, we again use that same relationship. Gauge pressure is rho GH, density times gravity times depth in the fluid. Crown Z is still at a greater depth in the fluid at the top of the crown, but if you were thinking it's crown Y because the bottom goes lower, good for you. You were focusing right there on the bottom of the crown at the lowest depth.
Okay, and here is the last question, which is our experimental design question. And it's multiple choice, so you at least have something to pick from. So a student wants to determine the change in density of a fluid or a liquid as a function of its temperature. So there's kind of your 2 variables that you're looking at. The student has various measuring devices and some blocks of known density and cross-sectional area. Which of the following is an appropriate experimental method to determine the relationship between temperature and density? And this one has 2 answers. So how would you measure the change in density as the temperature changes? So if you look at selection A, it says put a known volume of the liquid in a container and place it on a scale. Record the mass of the liquid as the temperature is increased. Sounds fairly legit. B says put the known mass of liquid in a container with a known cross-sectional area. Record the depth of the liquid as the temperature is increased. Also sounds pretty good. Put a block of known density of cross-sectional area on one side of a double pan balance and place a known volume of a liquid on the other pan while increasing the temperature of that liquid. That one sounds really good. And D says let a block of known density and cross-sectional area float in the liquid. Place the container of liquid on a scale and record the mass of the liquid as the temperature is increased. That one seems really difficult. I can't even imagine doing that. So in this case, answer choice B is going to be the best answer, one of the best answers out of these four. And we'll talk about the bad ones in just a second. Now, the second one that looks good in this case is using the double pan balance. So if I use the double pan balance, if I put a block of known density and cross-sectional area, if I know the density in the area, I can find the mass of that block pretty easily. And therefore, if I have a known volume of liquid on the other side, and it's all balanced out, I know the mass of the block and the mass of the liquid are the same. And I can increase the temperature of that liquid as we're measuring it. And if the density is changing, what do you think is going to happen to that double pan balance? Remember, this thing is able to go like this. So what's going to happen if the density is changing? It would be in motion.
All right, here it comes, the debrief. We hope you learned everything there was to know about pressure and about density. If not, you can watch this as much as you need to. One of the important key pieces that my students have asked me to stress is that all of these things are equivalent. 1 gram per cubic centimeter is the same as 1 kilogram per liter, is the same as 1,000 kilograms per cubic meter, is the same as a specific gravity of 1. All of those things describe water. And all of those units describe density. So converting between units for density is all about deciding what volume scale is most appropriate for what you're measuring. If you're drinking water, you're probably not talking about cubic meters of water. All right, so here's what we were hoping that you learned. Density is expressed in terms of mass and volume, that a fluid at rest exerts forces perpendicular to surfaces within that fluid, that fluids apply normal forces, that pressure increases as depth increases, that absolute pressure is the total of gauge pressure and any extra pressure on top of whatever fluid you're in, and that the specific gravity of a substance is the ratio of its density to the density of water.
And can you answer these two questions? If you had two identical containers filled with a known liquid, how would you determine the density of those two containers of liquid? And what quantities would you need to determine the pressure at the bottom of a swimming pool?
So here comes some practice questions for those of you getting ready for the AP Physics 2 exam. In which orientation will the box exert the most pressure on the table? I think this is one that we can discuss right now. In which orientation will the box exert the most pressure? I hope you're all thinking orientation Y. I know that's what I'm thinking. This one you should take a screenshot of. Grab a screenshot. We'll start with it tomorrow. A partially evacuated vertical cylinder. It's covered by a circular lid that makes an airtight seal. Think a tightly sealed bucket, and partially evacuated means the gas inside is at a lower pressure than the gas outside. So you have some data about the pressure. You have some data about the size of the lid. The question is, how much force will it take to open this bucket? And your hint is you're going to need to draw a free body diagram. You're going to need to show the forces exerted on this lid. If you draw the free body diagram really well, there should be 4 forces exerted on this lid, several of which you may never have thought of before. Mr. Eaton, can you take us through this one?
Sure. Last question that we're going to go over tomorrow. Be sure to take a screenshot and try to work these out before we get to tomorrow's lesson. This one's about a diver that's descending 35 meters below the ocean surface, and he finds an aluminum plate that's 1 meter by 2 meter by 0.03 meters. The diver attaches a cable to the plate. The specific gravity of the aluminum and the ocean water are 2.7 and 1.025 respectively. And your goal is to find the mass of the aluminum plate, the gauge pressure at that depth, the absolute pressure at that depth. Now, if the cable pulls up with a constant velocity and negligible friction, could you calculate the tension in the cable? And how would the absolute pressure change, if at all, if the plate is raised upwards at constant speed? And I guarantee you that you want to start part D and part E by drawing free body diagrams.
So grab a screenshot of that question. We'll start there tomorrow. And as always, thank you so much for watching us. If you're just starting to tune in now for the next series of review lessons, I hope this is useful for you. We're going to go through everything that's going to be on the AP Physics 2 exam. We'll have some more information about the structure and timing of the exam going forward. If you have any questions, you can check for all of your answers at the College Board's website. Thanks a lot, everybody.
Thank you, guys. See you tomorrow.